Okay, let's try to use. So I have 45 minutes, correct? By the way, yeah? That's the first. Right? Yes, yes. Oh. You have to make. Okay, then we'll push buttons later on, yeah? So I have this kind of tricky title, yeah? Powerspace and the bulk problem. And I start with this bulk problem, which, of course, is not quite mathematical problem, but rather scientific one, which I will not approach. I will be going from mathematical end. I will never come to this, but this is a kind of guiding light for what I'm saying. And the problem is, just imagine you have the following kind of situation. You're a mathematician, but you want to solve some problem of chemistry, yeah? And so you have certain vessels, yeah, with some unknown to you liquids, yeah? And you can mix them, and something happens, and there are dials, and after you mix them, it shows you something, right? And so you can make all these kind of mixtures, and you don't know what it is, but it's something like density or conductivity or whatever you can measure. And you have in your mind the idea that this substance is made out of little tiny things, yeah, like molecules. And you go on and you get these numbers on these dials, and you mix them in different ways. You have different numbers, and you want to figure out what are these constituents, what are these molecules. And this is exactly how chemists started. Yeah, they had no idea even of molecules. They were mixing at first in alchemists, and they were getting pure substances, and they're mixing them, and just something was exploding, etc., etc. And eventually we came up with the modern theory of matter. And the question is, if mathematicians could have done that, yeah, just without understanding anything, and in a way we understand nothing, we only see these numbers on these dials after all, right? We see it on temperature or density or whatever, and then we come up with the theory of matter, how it can happen mathematically, right? And so I believe you can do it. You can do it mathematically, just if you use some proper, very general principles and manipulate with these numbers, you can reconstruct back what was in there. However, it's even difficult to formulate, yeah, because you have to start with some modeling what are these little objects are. Yeah, this molecule, something unknown to you. And actually, many fundamental things about molecules you cannot quite get like that, yeah? So in science, you have some data coming from these bulk measurements. You measure some kind of averages, but sometimes you measure, if not individual atoms or molecules, but something in between, yeah? For example, if you look at the Avogadro number, right, something like 10 to the 25 or 26, I keep forgetting something like that. Do you know actually when and how it was first precisely measured? And so what would happen if you replace this 2 by 4? Yeah? And if it was 4, it would be quite hard to measure. And actually, it would be still very conjectural. And it is kind of quite interestingly, it's kind of a halfway bulk experiments, which it has long history. But who first, who was the first man who rather precisely evaluated the Avogadro number? You don't know? I think you never heard of him, probably. Yeah? It's Einstein. And it was his theory of Brownian motion which allowed to measure that. But the Brownian motion is an interesting way. So atoms are too small, you cannot see them. But because they are of the size of or molecules of 1 nanometer, yeah, something like to the -1, down to the -10 meter. But inside you may have particles of the size 10 to the -6, yeah, of 1 micron, roughly. And this you can see in microscope, because this number is comparable to the length of the visible light, yeah? It's 3 times bigger, roughly, than the visible light. So you can observe them directly in the microscope. And this, on the other hand, react on collisions with individual molecules. Well, not quite individual molecules, but into fluctuations in the density. And observing that, it was the first sharp measurements of the Avogadro number. It was the first really sharp confirmation of atomic structure of matter. Though actually this has been done before, actually by Maxwell, by cruder and purely bulk measurements. So there are all kind of experiments you make in physics or in chemistry, which you can interpret kind of mathematically on what scale they're being done. And so my point today would be what you can say about bulk of matter. I'm sorry, what you can say about individual particles if you know them, how they behave in bulk. And then you have to formalize it mathematically. And the moment you do that, you can unfortunately go very, very far away from physics or chemistry or whatever. But this, I think, quite amusing question to make this formal chemistry, which may be not useful. Chemistry is too developed to make any use of that, but it may be useful for other subjects. But now, coming to mathematics, so what happens? In a very simplistic way, when you have many particles appearing and they say all the same particles, so you start with some space x, yeah? And space, for the moment, just I don't say what it is. And then you take it, you multiply it by itself. So you have something and you repeat it many times. And the product, meaning Cartesian product. And so this, you can think about that as a configuration space of the phase space of a particle. Imagine the particle kind of interesting enough, yeah? It's something like this line, it may be in this position, or it may be in this position, yeah? So it's certain space, and then it flow in solution, so I have many copies of that. And that's actually also characteristic of systems we observe in nature. If something happens, and happens lots and lots of times, yeah? That's kind of characteristic for natural sciences, like very unlike history or literature, where each phenomenon is unique. And then, therefore, you cannot study them systematically in a mathematical way. But here, if you have some molecule, and you observe some molecule somewhere, be sure it will appear billions of times. And so something can appear billions of times. And just for the moment, it's just a set, and you multiply it by itself. And then you look at this product. And this seemingly simple operation creates kind of immediately rather amusing structures, right? If you take just 2 points, yeah, whatever, it cannot be anything simpler. And you multiply it by itself. Then you have this square, and you do it again, and then you have a cube, yeah? And then you do it again, and you have cube and high dimension. And eventually you have something infinite dimensional when number is very large, right? So you have this 0, 1 point thing. And then you repeat it many, many times. And here there is this number n, how many times you repeat it. So yes, immediately, if you're kind of a mathematician kind of brought up in a kind of modern language, you know this is just a set of 2 elements, yeah? And this I repeated n times. So if it was 2, so what I see is this square, yeah? If it's 3, I have this cube, etc. But then already you see something wrong here, yeah? So of course, we always, mathematicians write that, yeah? And this, of course, nonsense, yeah? Because you cannot take set to the power of a number. It's just wrong. Yeah? We know it is wrong because it is a number is a kind of not an object of this kind of mathematics. What you have here, in fact, you have some set again, and this is a kind of big difference. In a second, we see what is the difference. Now, what I mean that this exponent is, again, somebody who has definite structure. It may be the structure of a set or structure of something else. And in this model, you may have this ball, and there you have these floating particles, or these particles may be in a lattice, yeah? They can make a crystal. And the number, of course, may be the same, but the bulk of matter you get will be quite different, right? So you cannot say that this is a number, and this must be a set. And then set, meaning something having structure. You have to specify the structure, and just what I say will be kind of side remark, just showing how non-trivial it can be already for this very simple example. Just to have some respect for this seemingly simple operation of multiplication. So what happens categorically? Just imagine you have a very simple kind of situation. You have a 3-point set. And just to give it a structure, we have to indicate what maps we allow. And so we can see the sets, say finite sets, like 3 elements is good enough, and we consider 2 types of maps. Identity is necessary, must be there, it's a category, and we only allow constant maps. Okay? So we have 3-point set, and it can be mapped to itself by identity, or everything goes to a single point. And this is a rather boring object, yeah? There is apparently nothing interesting there. But if you go to the product, and so we take this 3-point set into the power big set, big finite set or infinite set, this becomes kind of a cube, yeah? But now if you do it once, you have this picture, then you just add it again, again, and again. Now, so what happens to this map? So we have this map of my background set to itself, and you can see that all maps it generates in this product. But then there is also this set, yeah, also involved here. So it is a function in 2 variables. Here we only allow the map which I described, and here it will be just all maps between sets. So you kind of mix these 2 categories. And it's what kind of structure you see in very big products. For example, what will be possible images of these maps? Look at the images of these maps. And then what you see in this picture, it will be this, and also diagonal. Right? You have constant maps times identity maps. Right? So you have this line, these lines, and diagonal. If you take cube, it will be all partial diagonals, and kind of all direction, all partial diagonals. So whenever you have to map F1 and F2, you can take their product, right? You have kind of something in 1 power times this power. So you have this power plus, no, maybe star plus this star, and you have some map attached to this, some map attached to this. You can multiply them. And if you look just at the image of this, you have this kind of projective geometry. You have huge product. You have this huge product. And just, again, eventually, I want my set to be the infinite countable set. And in this very big space, this structure of interest is defined by these directions. So what can you say of interest of that? So if you just start with this set, 1, 2, 3, 1, 2, 3 points, take this infinite product, we have this semi-group of transformation, which was very trivial, having 4 maps, identity, and 3 constant maps. But here you have all their products and all permutation of this. Yeah? So you have a much bigger semi-group. And this semi-group already has kind of properties which are not so obvious. And the essential feature of this is a kind of famous theorem of van der Varden, says the following, that if you take action, now we have this very big product space. Yeah? So 1, 2, 3. I say infinity, but infinity meaning a set. And there is this huge group acting on this, a semi-group, I'm sorry. You have this constant maps, diagonals, and permutations. And it acts on this space, and therefore it acts on the space of its function. So you can see that functions with value, say, in a finite set. So it's now even bigger, something bigger. But I think this now my background space, all these products, and I take functions with very infinite set. That's in turn, again, some compact metric space. These things operate. And the van der Varden theorem in this language essentially says that every minimal set is fixed point. Right? That if you take any subset invariant under the action, which contains no smaller closed subset invariant, you have to say closed slightly carefully. Yeah, it's not closed in a kind of quite obvious sense, but closed under kind of categorically closed subset. Then it will be just constant. And in the usual sense, van der Varden theorem says if you divide integers into 2 subsets, then one of them contains arbitrary long progressions. And this is a kind of essentially extract from that. So it says on one hand that when you go to this product, you obtain objects with properties which you cannot quite see, which don't show up for individual set. Right? So just there are artifacts coming from the fact that you take very big number of objects. And this you have to keep in mind. You have to kind of always kind of filter this away if you want to reconstruct original objects. Now, so this is kind of, on one hand, and this, by the way, not fully understood. Yeah, we don't exactly understand in which categories this kind of theorem takes place. There was kind of very big development recently, especially due to Gowers, but this structure is still rather mysterious. Yeah. So what happens? What are the properties of the semigroup, and how it acts on function spaces? But now look at another example, which is of opposite nature, showing that when you go to the power, sometimes you even gain something about your original space. And the example which I keep kind of repeating in repeating in many lectures, because amazingly enough it's not very well known, is a Hölder inequality. There is a classical Hölder inequality between LP and LQ norms of functions. And this inequality, I don't even remember, and you don't have to remember if you say it correctly. But now I just want to formulate it correctly, and again, the remarkable thing is that you can see it just by this conception of power without any computation. So what is this inequality? You take integral over some space of functions, say f1 of x to the power alpha 1 times f2 of x to the power, maybe I write beta, keeping tradition with physics, yeah, etc. to the power alpha n. And so you want to know, I'm sorry, beta. Yeah. It corresponds to inverse temperature. And I want to know how this integral depends on these variables beta. These are given functions, and this you think about the beta as variables. And the Hölder theorem says you take log of this, or maybe minus, I never know. It will be convex, or concave without this. Yeah, this always beats me. Yeah. But again, it will be clear from the proof. So there's classical Hölder inequality in the form, I think, going back to Gibbs. And so how to prove this? Yeah, so I just want to suggest a proof. Again, probably going back to Gibbs or to Maxwell, which doesn't require any computation, but only the fact that there is some universality of this formula with respect to product spaces. And the remark, the property which we use is, so it was living on a space X. But now let's go from X, for example, to X plus X. So whenever I have function here, and I have the same function here, when I go to the product, I just multiply function, right? So I take f x1 times f of x2, yeah? This becomes function of the product. So I'll just do this for every function. So I go from x to x plus x. Then everything is being multiplied, yeah? And these just two things add up. So I take log, and actually there is a reason why I take log. You could keep it multiplicative, but just easier to say, yeah, just to keep to the terminology. Otherwise, you have to say it would be log convex, yeah? So this quantity multiply, integral multiply. Therefore, you have the same function in betas. It's just multiplied by 2. So you just multiply, if you go to the product space, the whole thing multiplied by 2. So whatever you prove for the original, for the new thing, the same will be true for the product. Okay? So that's kind of trivial. But then just keep doing that, yeah? And again, nothing happens. You just multiply it, so this integral multiplies by n. So what do you gain? But what happens when n goes to infinity? This number of terms goes to infinity. You can use the law of large numbers. And the law of large numbers tells you that all these functions become eventually constant, or rather constant each on its own support. And if you have constant functions, of course, if this function are truly constant, this will be just linear function, right? What is the integral? Just the value of the function, right? So the constant will just become coefficient here, so they become constant. each of them constant on their own support. So the only here they are linear, and this term disappears. So, and therefore the function will be called convex or concave, whatever. This integral of the product will be smaller than the contribution of each of them, because these things die away, right? So you reduce in this way this general theorem to the special case when functions, each of them constant on its respective support. Yeah? And then it reduces to the case when functions are constant. And when they're constant, it's obvious. And so, but again, because it's very simple proof, except that you use the law of large numbers in its weak form. So, now weighing how it enters in a kind of more sophisticated mathematics. So just again look at now 3 points, but now imagine this being probability space. So there are some weights here, right? We can say 1/4, 1/4, and 1/2, and then the entity which one likes, so that 3 weights P1, P2, and P3 is the entropy of this, yeah? And this, like this exponents, has this property that you will have 2 probabilities, finite probability spaces, and there are weights here, and you multiply it by this one. So I have a matrix, fill in with products, Pi, Pj. Then this quantity is multiplicative under this operation. And now you want to understand in what sense you can reconstruct this out of the product. And this is slightly more interesting. So I have, say, finite probability space X, and I take its infinite power, but this infinite must be understood what it means, and in what sense you can reconstruct this entropy in terms of something of this space. And one way to do it, and this in a way can be thought as a definition of the entropy, is that I consider because the high power when n eventually will go to infinity. Now we have kind of table with numbers. But again, with the law of large numbers, almost all of them will be constant. And you will have almost the same value. So on one hand, entropy, so it's multiplicative. So entropy of x to the n equal n times entropy of x. So I put n here. And so I have this formula. On the other hand, by the law of large numbers, here almost all points are constant. And entropy of such space where all entries are constant is just log of the number of the points. So on one hand, it interprets entropies as limits of cardinalities of essential points here, those which contribute to it. And this one thing, but that not exactly what one wants in here. Because the problem which was the point of view was promoted by Shannon and then by Kolmogorov is somewhat different. So what is actually this infinite product, right? So when you have this finite measure space X, and you take this the infinite power. So what is this object? So we know it is again a probability space, yeah? But how you can see it, how you can see that this probability space, just without knowing what probability space is, but only knowing what are finite probability spaces. So there are finite probability spaces as finitely many points with weights. You go to infinity, to this power, and in order to define the structure, you have to go kind of through measure theory. And this kind of what you don't want to do, right? We pretend we don't know the things. So one thing you can say, this space being infinite product, and so each n plus 1 goes to xn, and so we have this infinite tower. And categorically we can say, we have projective products of these objects. Of course, we have to say what are maps between finite probability spaces, and you think about them as each of them being a bunch of stones, and then you just have you can organize them into smaller groups, just transforming the stones, meaning the measure preserving maps. And so when you go to this limit as a measure space, again, because you already know, you obtain just the standard Lebesgue space. However, if you use this kind of projective tower definition, you don't recapture all the morphism in the measure theory. You only recapture continuous maps. However, if you slightly soften your approach, and when you work with finite spaces, you allow small errors which eventually go to infinity, and you make this kind of a softer limit in this category of projective limits, you do recapture the whole category. So you can say that category of measure spaces is kind of almost like projective limit of category coming from finite measure spaces, but modulo some weak limit property. Yes, but it's kind of, everybody kind of can see how it happens. Any measure space can be partitioned into finitely many kind of subsets, and partitioned finite and finite. Therefore, it is this kind of projective limits. But when you consider morphisms, you may have errors. And this is a kind of just absolutely obvious, but you don't have to say it. Yeah, in a way, you can define measure space in this way. And then you have this, and then you have this entropy. But now, in what context this entropy can be reconstructed? So, what structure you need in the power space to reconstruct in the infinite power space to reconstruct the entropy? So, if you have finite power, I just take this entropy and divide by n. But if I don't know this number n, it's not so obvious, yeah, because I have this just infinity. I don't know how to normalize. And then you need something in this infinity. Yeah? So you cannot do it, and this is exactly the point I want to make. It's essential what this infinity signifies. So in physics, this infinity, it may be either particle in the space, or it may be particle in the lattice. So they may freely moving in the space, or they make something in the lattice. But in either case, this set, this infinite set, carries additional structure. Here is structure saying which points are close and which are far. So it's the structure of the Euclidean space. And here the structure of the lattice. But in either case, what's essential that there is an action of extra group here. And say in the case, if you have three-dimensional lattice, you have these groups operating there. So as I was saying, one category involved, just which morphism we allow for underlying space, another, what are morphisms here. And in the case of, say, crystal, we have action of this group. Once you have this structure, for example, of the group, you have a natural exhaustion of this lattice by bigger and bigger sets, something like by balls or whichever, so-called Ferner set, for example, by balls. Therefore, you can approximate this infinity by finite n. And then you just make this kind of the following, pronounce the following words. So entropy is multiplicative. And as a function, it is continuous. Therefore, it survives this limit. And yes, if you go through that, you come to the theorem of Shannon-Kolmogorov saying that the entropy of Bernoulli scheme, what is called Bernoulli scheme, equals the entropy of an underlying space. So if you have, for example, this group acting on the infinite product, like 3-point space to the power of that, the entropy of this dynamical system equal to the entropy of this space. Yeah? So the point what I want to make is that you don't use any kind of measure theory or partitions or whatever. You just absolutely formal manipulation with categorical property of the product. And non-trivial point is this, originally this function had this multiplicativity property. Okay, now, so how much time I have? You're confused.
You have 10 minutes.
10 minutes, yeah. Now I can come to kind of the question which I find more interesting is, which I as follows. As we were speaking about the bulk of matter, one typical measurement which is being done is done by calorimetry, right? So you have your solution of a known something, and you heat it, yeah? And you see how much heat you need to raise the temperature. As temperature goes up, right, the amount of heat needed to go by 1 degree changes as a function of temperature when you do it. And typically, the hotter the temperature, the more you need to heat to get extra degree. So the reason for that, and this is kind of was known for simple gases for a long time, we have, say, monoatomic gas and two atomic gas, and they have different specific heats, yeah? And this, because you have more degrees of freedom. So now I want to understand this effect, that you have a bulk of matter, which each molecule has certain degrees of freedom, and how bulk measurements tells you how many degrees of freedom are there. Right, and that, I mean, the problem which is systematically used in chemistry and biochemistry, you understand the structure of molecules by looking at the specific heat, how much heat you need to go from 1 degree to another. So what it would be from a mathematical point of view? Again, from very limited mathematical point of view. So I'll do this again. Now we can come to the class of problems which are much closer to what is more open and from certain angle is more interesting. So now imagine the X is truly a space. Yeah, it's not a finite set like measure space, but it's something like metric space or topological space. And again, you go to this high power, and this goes to infinity. Or it may be infinity, but again, it must have some underlying structure of this infinity. And what you want to understand, what happens to the topology of that. So how much, for example, by looking at this infinite power, Cartesian power, you can reconstruct topology of the space itself. And this already, kind of, this topology carries certainly much more juice than just set theory. If you take the simplest kind of interesting space like circle, and you take it to large power, you have this high-dimensional torus. And high-dimensional torus is not topologically easy at all. And so one point is if you can reconstruct dimension. So just exactly this dimension is what enters the number of degrees of freedom per molecule. Can this be reconstructed or not? And so what I want to say is up to some degree you can do it, but from some moment on it becomes not so apparent. So if you follow this logic of entropy, so what we can do is as follows. So on one hand, we have this n, and imagine this n being this infinite number, this infinity being a lattice, like in Z3. So you think about atoms being positioned along the lattice, this three-dimensional lattice. And each of them has some internal degrees of freedom. So in each of them you have a space X. It's either configuration of the phase space of this molecule. So it's an infinite product of these spaces. But it's not just infinite product. This infinity is this group. So you have this big space, X, and you have an action of this group. And the question is how much this data, so it means what kind of bulk measurements invariant under transformation of the group, which of them and how much from them you can learn about individual space. So first, about dimension. And with dimension, you can do that. Dimension has the same additivity property as log of as the entropy, right? And from that reason, this formal scheme which I described applied here. So essentially what you do in this particular example, you consider big set in your lattice. You take this kind of partial product, take its dimension properly understood. You must be slightly careful. Divide by the number of points and go to the limit, and that will be quantity which depends only on how this group acts on this X. And this is a quite general scheme. So it gives you well-defined number of degree of freedom per site. And that and this is not difficult. However, so where it becomes interesting, and topology of this, like a product topology, is not that complicated. However, what is not so clear, what are other kind of invariants can be seen in a similar way. So dimension is a good invariant because dimension of the product is multiplicative or additive, right? So it behaves like entropy. And so, but what are other kind of robust enough invariants behaving in this way? And of course, you know, there are some invariants which behave in this way. For example, early characteristic. But the early characteristic has unpleasant property because there are pluses and minuses there. And when you go to infinity, to the infinite limit, yeah, it doesn't kind of converges, yeah. So it is, and actually it is not. So it is not clear, and this is a kind of a question. So what are reasonable invariants of a space X such that when I take it to the power n and divide by n, the limit exists and is being neither infinity or 0 and become invariant of the space itself, right? And moreover, of course, we want this to be compatible with the just maps between the spaces. And so let me formulate a specific question in this regard. So if you have just simpler space, just the interval, and you start multiplying it by itself, you have this cube. Yeah, and this cube, of course, just you're getting bigger and bigger, but still you have only one cube. And then, just for every space X, you may start covering it by cubes of dimensions, say equal dimension of the space, and define kind of the minimal number of cubes needed to decompose the space into cubes. Yes, then you use this as an invariant of your space, and then go to the limit. And this is sub-additive quantity, so the limit exists. The question is if this limit is 0 or not, for at least for some spaces. And So sometimes, say, for example, what you can prove, just the point is about unsatisfactory. If, for example, x, in the example we know where to look for, if you have manifolds of negative curvature, for example, of even dimension, then you can show, I'm sorry, of constant negative curvature, of even dimension, then you can show this invariant non-zero. But if I is a variable curvature or it's odd dimension, it's unclear. I just don't know. Right? So it's kind of quite simple natural invariant. You just use what you know for cubes and kind of force it to arbitrary space. And then you immediately run into kind of problem which is unclear. And this is a certain way to measure the topological size of the space. It's more subtle, more refined than the number of just degrees of freedom. Do you have another 2 minutes? Okay. So it's one question. And I want to conclude with another question. Well, actually, we took maybe related questions. So first, I want to reiterate an old question by Serre, which was answered in a way, but still quite open, and it is follows, which I don't have time to explain why it is closely related to that. And the question is follows. I have X finite cell complex, and I consider the base loop space of this. And you can see the Poincaré polynomial, kind of Poincaré series of this. So it's the sum, it's Betti numbers of this creature, bi t to the I. The question is, what kind of functions you get here? So Serre asked at some moment if this is always a rational function, and then counter examples were found. However, if you look at this counter example, they're kind of remarkable function, like Ramanujan type function, beautiful kind of very well organized creatures. And apparently all of them have kind of meromorphic continuation and just they're not rational, but they're very distinguished transcendental functions. So what kind of function we have here? So you may expect, if it's simply connected finite complex, you come to some kind of remarkable classes of functions, but we don't know what these functions are. So and another question which is closely related to that, but probably easier, is of very similar nature. I consider, again, this product, but I had no time to say it more. Of course, the product's only the beginning of the story. The interesting thing when a particle interact. And so inside of this product, you consider some subvariety, say y, obtained in the following way. I just write one equation, p, so this variable xi plus 1 equals something. So imagine this x being projective space. And this is just generic polynomial of certain b degree. Yeah? And I repeat the same everywhere along this line. And so for every n, I have this non-singular algebraic variety defined depending only on 3 numbers, on this topologically, on this number n's and these b degrees. Well, say dg. So it's some variety depending on n, g, and the block I took this n. So I have the 3 numbers that define you topologically a certain variety. So for each of those, I write its Poincaré polynomial. It's certainly, so there are 3 numbers, n kind of being fixed. Put it here, and here is g and n, and so I write s to the g and g to the n. And which is infinite to n, yeah? So this sum. So I have this function in 2 complex variables. So what kind of function you get here? So it's a unique canonical function. It depends only on 2 numbers, g and n. I'm sorry, what am I saying? It's a Betti number. I'm sorry, Betti number of dimension I, and so I better to say it in reverse, yeah. So up to each n, you write Poincaré polynomial. It's some polynomial. And then there is parameter n. So there is Poincaré polynomial depending on n, and then you write it to the n and you take the sum. Yeah? So this polynomial in 1 variable, so the resulting infinite sum is function in 2 variables. And what kind of functions you have? You can show something about them, but again, I don't know if they have analytic continuation of this function, kind of well-shaped, etc. And it's very similar in nature, this function, the one which appears in this problem. And again, strangely enough, it's kind of very simply described algebraic variety, but when you try to directly compute, at least when I, with my limited knowledge, compute cohomology, it's become tremendous combinatorial mess. Yeah, you kind of, in a way, you see perfectly what it is. But it's combinatorics with every step getting more and more complicated, ramifies, and you need some techniques how to organize it, and this, I think, this kind of quantities may be relevant to understanding this multi-particle systems, yeah, because this is the easier thing you may ask about them, and already you run into non-trivial mathematics. So, and the point, again, I repeat, in the last question, is as follows. So I have this graph. I want to really out of those terms. It's a very simple graph. And you have variables here in each of them, running in the same space, in same algebraic variety. And then there is equation between them, always the same equation between this pairs of points. And so you repeat the same equation. So it's very simple kind of chain of algebraic equation where the same equation is repeated n times. And then you give algebraic variety, and in a way it depends only on degree, but how its topology develops with the number of the terms of the chain is unclear. You can, in this asymptotic expansion, you can expand it. It grows exponentially, and the first term is easy to guess. I mean, because you can compute, of course, the early characteristics, and this apparently the dominating term, but it's unclear. So, okay.